Let's go ahead and continue this section by taking a look at an example calculation of an integral. And this time we're going to try to take advantage of some of the geometric facts that we know in order to do this computation. But we also want to get a little bit of practice in with some of the words that we just learned. So we're looking here at this guy. And remember, the way that we read this is this symbol here is our integral symbol. So it says take the integral from 1 to 5 of the square root of 4 minus x minus 3 squared plus 1 dx. So we have a couple of vocabulary type questions first. The first one is just asking us, what is the integrand? So remember, the integrand is the thing that we are integrating. So for us, it is going to be the function square root of 4 minus x minus 3 squared plus 1. This is the function that we're finding the area under its curve. Part B is asking us what are the limits of integration. So those are going to be the numbers 1 and 5. Limits of integration being the x values between which you're finding the area. Last, we're asked to actually do the computation, and it certainly shouldn't be obvious just by looking at this how to do the computation, but maybe we want to think about what exactly does this graph look like. So we want to think about having kind of this goal in mind of graphing y equals root 4 minus x minus 3 squared plus 1. So this certainly doesn't look maybe like a very familiar function type, but we can do a couple of tricks here to make it look a little bit more familiar and to give us a handle on what's going on here. So I'm going to start by taking this equation that I have and subtracting 1 from both sides. So I'll have y minus 1 equals the square root of 4 minus x minus 3 squared. And then I can square both sides because the square root is kind of what's giving me trouble right now, so it would be nice to get rid of it. So I can square both sides, and I get something that looks like y minus 1 squared equals 4 minus x minus 3 squared. But if I add this x minus 3 squared to both sides, I end up finding x minus 3 squared plus y minus 1 squared equals 4. And this looks pretty familiar. If this were something just like x squared plus y squared equals 4, we would know that we would have here the equation of a circle. And in fact, we do have the equation of a circle, and we need to remember our 112 background, which tells us exactly that this is a transformation of a circle, and that this minus 3 and this minus 1 here are telling us what the center of that circle is. So we're going to get this information here that this is a circle with center at the point 3, 1. So we're getting the x value of 3 from the fact that I've got x minus 3 squared, y value of 1 from the fact that I'm looking at y minus 1 squared. So we know the center of the circle, and we know that the radius here is 2, because 2 squared is 4. The right-hand side tells us what the square of the radius is. So cool. So this is pretty nice. But we need to remember something here, which is we need to think about the fact that we started with a function, and a circle itself certainly isn't a function. It fails the vertical line test. So what's going on here? Well, notice that the equation that we started with is telling us that all of my y values are going to be at least 1. Namely, because this square root here is the positive square root. And so it's going to spit out numbers that are at least as big as 0, and then we're adding 1 on the end. So we're going to get y values that are at least 1. So if my y values are all greater than or equal to 1, and the center of my circle occurs at this point 3, 1, then the actual circle that I'm looking at here, let's put it up here. Let's see, we've got y value 1, we've got an x value of 3, center of the circle here. My y values are all at least 1, that's going to tell me that what I'm graphing here with this function is the top half of the circle, where all of my y values are in fact bigger than 1. Since I have a radius of 2, that means that I need to go left 2 units from my center here. So here's 1, here is 5, and then I have a nice semicircle here. Great, so I've drawn a graph of my function y equals square root of 4 minus x minus 3 squared plus 1. But now I need to figure out exactly what the area under the curve is. So remember, area under the curve means area between the curve and the x-axis. So when I'm looking for this area here, I'm going to have area that lies both underneath this circle and down here in kind of this empty space. So in order to compute this area, we need to split this up into a couple of different pieces. We need to split it up into the semicircle, which is something that we can compute the area of, and the rectangle that lies below it. So let's take a look at kind of what's going on here. So this blue thing that I'm outlining here is the rectangle. We certainly know how to compute the area of that. And this red piece here that I'm shading in is the semicircle that we're going to want to talk about. Because this integral that we're interested in computing is this integral from 1 to 5 of our function square root of 4 minus x minus 3 squared plus 1 dx. And this area is a combination both of the red areas and the blue areas that we've drawn so far. So this is going to be equal to whatever the red area is, we can call that A1, plus whatever the blue area is, which we can call A2. So that's the total area between the curve and my axis. Now, the red area we can compute because we know it's a semicircle. We know that the area of a circle is pi r squared. And so what we're looking at here for the red area is pi r squared over 2. Well, let's see. So the radius of this circle we know to be 2. So this is pi 2 squared divided by 2 because we're looking at that semicircle. The area of the blue rectangle is given by base times height. Its base length is 5 and its height is 1. So we have the blue area here is 5. And so the actual integral overall is going to turn out to be this pi 2 squared over 2 is going to be 2 pi plus 5. So we have here a nice integral calculation that we were able to do because we know something about the areas of circles and we know something about the areas of rectangles. Certainly if this weren't some nice shape that we were able to look at geometrically and have area formulas for, then we would have struggled a little bit more with this computation. But for the time being, this worked really well for us, and we were able to actually take this integral.